really ever tried to do it because it's so computationally intensive and it's so complex to implement into code. But I'll be explaining how we tried to imitate FTC using a neural network and then how that slowly evolved into us using that for path following, path generation, and motion profiling. So first of all, a quick explanation about what MPC is. There's three main parts about MPC, and the first part is the state space. And without going in too deep about what the state space is, essentially all you need to know is that it's a mathematical model of the system. And when the MPC is solving, it uses that mathematical model, solves a bunch of equations, and finds the best input. And then the second part you have is the cost. The cost is sort of like, it's like penalizing the things you don't want. So if I want to get from point A to point B, I can make the cost higher on the strafing part. So I don't want to strafe going from point A to point B, I want to turn and then go straight. So that's sort of what the cost does. But that's like pretty basic stuff for control theory. The reason why MPC in particular is so special, why it's so, I guess, mystical in MPC, is because of how it optimizes. Unlike LQR, which runs only once, or PID, which runs only like once every step, MPC, what it does is that for model predictive control, it predicts into the future. So imagine if my prediction horizon is 10, what I'm doing is at step 0, I'm predicting 10 steps into the future, calculating everything through the mathematical model and doing like college level algebra or college level mathematics. It calculates everything 10 steps into the future and then does that for every single step. So that's why it's so good, but it's also super mathematically computationally intensive. So like I said, it's pretty hard to implement in FTC. I think, to my knowledge, there's only been 2 teams to ever do it, and that is the first guy on the right. His name is Jay Wong. I don't know what team he's on, but he was from a long time ago. He's sort of a legend, and he made it in simulation and showed how good MPC can be. He coded everything from scratch, but the problem was it was only in simulation, and then when we ran it, the loop times were like 1 to 4 seconds. So imagine if you're running your robot in FTC, you can't be having 1 to 4 second loop time because you have to be updating every single time. You have to be updating your loop, your localizer, and things like that. And then another team that's done it is FTC Curiosity, which is a pretty well-known name. And what they did was basically they took code from C and then put it onto their robot, which made it really fast. But the only problem with their implementation, there's not really a problem. It's just really hard to code. And it's also really hard, especially for new teams, to implement that type of thing. So, next slide. In general, the only things you need to know about FTC is that one is really, really, really good at doing these types of problems since it recalculates every single loop and it looks into the future. It's one of the best, if not the best controller for FTC, but the main problems are that it's super expensive and it's really hard to code. So, if you go to the next slide. Our main goal with this was to try to reduce that. And how we're going to do that is we're going to use a neural network. And essentially what we're going to do is if you imagine MPC as a box, we're going to take that box of MPC and then try to use a neural network to replicate exactly what MPC is doing. And then what this will do is it will not only reduce computation time since MPC takes forever to run, it will also make it a lot more easy to implement. You don't have to code any of the math since MATLAB can do all of that for you. So, like I said, this is basically just reiterating what I said, but MPC is really, really slow, and a neural network will be really, really fast, especially since we're using TensorFlow Lite and we're not using it for image detection. Usually when you think of TensorFlow Lite, you think it's super heavy, but those are for image detection things, and they have input layers of like entire images. You have to count every single pixel. But in our case, we're using a super lightweight model on TensorFlow Lite, which is a lot more optimal than just running MPC by itself. So now that you know what MPC is and what our plan is, I can explain like how we implemented it. So first, what you have to do is we're using MATLAB for all of this. We have MATLAB make a multi-stage nonlinear MPC model. And that's just basically a form of MPC that allows us to customize it in any way we want. So as you can see on the graph, that's like a sample path. So we start at 0, 0, which is the path in like the middle around there. And then we go to the first green dot, and then we go to the second green dot. So that's just imagining like a robot going from one point and then to the second point. And as you can see, we custom made our cost functions. And like on the first step, it goes really fast. You can see like the gap is bigger, and then as it gets to the second or the first point, it slows down. So that's an example of what FTC does, and that's an example of generating a task from MATLAB. And then after that, that's just one example. When we want to train a neural network, we have to make a ton of examples. So I think this one was 500 examples. It took like an hour to run, and it has 9,000 different data points. And what we do is we take those 9,000 different data points, and we input them, or we use them as training data for the neural network. And then the neural network takes those inputs and tries to replicate those outputs. In our case, the inputs are where you are currently, the first one you want to get to, and the second one you want to get to. And then the outputs are the ideal velocities in X, Y, and theta. Yeah, and then this is what our training looks like. Essentially what we did was we just took all of our data, and then we plugged them into, well, MATLAB has its own trainer, but we trained all of our data into a neural network, and this is what our training looked like. This is something called knowledge distillation, where essentially we're taking a parent model, which is, in our case, it's an MPC model, and we're making that the teacher, and the student is the neural network. So that's sort of what the basis of imitation learning is. We're taking one thing, and we're imitating it with the neural network, which takes out a lot of the time complexity. And then, so this is sort of the results page. This is what it looks like. The red dots on the left side, that's where the MPC tells it to go. And then the black dots is where the neural network is telling it to go. So as you can see, the black dots don't follow the path exactly, but that's sort of a trade-off that you have to make. As you can see in the top right, the MPC has a following accuracy of 100%. Our neural network has a following accuracy of 90%. But the biggest thing is that we went from 4 seconds loop time down to less than 5 milliseconds. So we're turning something that is like super optimal, and then we're making it possible to run on a robot by slightly reducing the accuracy, but still having it accurate enough to where we can run it at a small loop time. And then once we have the MATLAB model, this is more about how we go from MATLAB to our robot. We just turn it into a TensorFlow, turn it into Python code essentially. And MATLAB can do this for you. It turns the code from your MATLAB, it turns your model into a TensorFlow model in Python. And then after we have our TensorFlow model, we turn that into a TensorFlow Lite model into Java, and then we can run that on our robot. And then this is part of like where we reduce the complexity. We don't have to code any of the MPC ourselves since we're just using the neural network. All we have to do is we take our localization, which is the roadrunner localizers, and then we add a feed-forward step to make the velocities match what we want it to, and then we have everything be field-centric. We load the TensorFlow Lite model, and then everything should run smoothly. So this is what the results look like. As you can see, one thing that I want to point out is since we're running a neural network, it sort of acts like a closed-loop controller. So if I move it, you can see in the left or the right. If I move the robot, it moves back into its position since it's acting as a closed-loop controller. Every single time, every single like less than 5 milliseconds, it's running over again. That's what the results look like. It's pretty solid, but there definitely are some improvements that could be made. I think I'll talk about that next slide.
What feedback sensors are you using like that?
We're just using, we're just using the localizer. So we're using 2 odometry wheels and the eye view. So some future improvements are, like as you can see in the video, there is some overshoot, and that's mainly because mechanism wheels are known to be super slippery and not have that much traction. So if we can include that in our model, in our FTC, we can basically have like a close to perfect, a near perfect model. And that will improve not only our path following, but it'll also improve like our neural network learning. And then our second point is obviously we can improve our neural network learning. Like I said, even though we made it like pretty accurate, we made it like 90% accurate. If we bump that up to 100% and keep the loop times really small, this would be essentially like a really, really competitive follower for MPC, or for FTC. And then another part of this project, it's not just about neural networks, or it's not just about MPC, it's about basically anything from MATLAB. So if you know anything about MATLAB, it has like tons of different libraries. You can do LQL, you can do hole placement, you can do MPC. But basically with this pipeline, you can bridge anything from MATLAB, which is offline, and then you can use a neural network to bridge it to FTC. And then you can use basically any MATLAB control theory, turn it into FTC usable on your robot. So yeah, that's my project. Thank you. If you guys have any questions, I'll be happy to answer them.
So I think we can take one person and one remote question. So I see one hand in the back. I'm going to go ahead and bring the mic to you, and you can ask the question.
So you mentioned that mechanisms don't have much like good traction, right? It's slippery. Would swerve pods be more viable, and would it technically work with your neural thing?
Yeah, because all we're doing is we're taking the position you're at and telling it like what your x velocity, your y velocity, your theta velocity should be. So if you can figure out like the kinematics on the swerve, you can tell it like x velocity, y velocity, theta velocity. This would totally work for that, and also you have more traction.
All right, and we can take, I already see one question in chat online. So Joshua asked, at what step of the EDP do you code the MPC, or is it something that's worked on throughout the EDP?
What's the EDP?
Engineering design process.
Oh, at what step of the engineering design process do you code the MPC? Oh yeah, so one thing about this is we're using MATLAB. So MATLAB is basically just a control toolbox that's used in industry applications, and it has basically everything for you. You can use MPC, you can use LQR, and all you have to do is you create the model, and MATLAB runs the math. It runs the math for you. So all you have to do is put in your model, put in your cost, and then MATLAB will optimize it for you. So the thing is, you don't have to code the super complicated math expressions because MATLAB, the industry, yeah, it's basically done it for you.
All right, everybody give it up for Nick one more time.